Okay, sorry I'm slow getting started. Couple quick announcements. Number one, I'm catching a plane in a couple hours and will be gone for pretty much the rest of the week. So Erica will be lecturing on Wednesday and Friday. She's planning on recording it on her computer and plan to put it on YouTube as usual, although we've not tried it yet with her computer, so there's a chance it may not happen, so you've been warned. And I obviously will not be having my regular office hours this week, but if you have questions, you're welcome to email me, or we can set up a time to talk on the phone or Skype or something like that. Second announcement, I keep forgetting to send out the email about the final, but the very limited feedback I've gotten thus far indicates that so far it's been people prefer the idea of writing an RO3 to having a traditional final, but like I say, based on a very small sample size. So I'll try to send out an email. If most of the class is totally terrified by the idea, we won't do it, but like I say, I'm trying to make this as relevant to the bench science people as possible, and the bottom line is knowing how to write a grant will probably help you a lot more in your future career than a traditional final exam. But yeah, we'll see. Anyway, today, multiple regression. If you'll recall regression from before spring break, it's basically methods where you have a response variable y, a predictor variable x. You want to be able to answer the questions, is there an association between x and y that's greater than you would expect to observe by chance? Or the question of, given a value of x, what's the most likely value of y? So today we're going to try to extend that to the situation where we have more than one predictor variable. Say the outcome is, oh, I'm trying to think of one. Say you have an outcome of heart disease, which isn't a good example because that's probably dichotomous rather than continuous, but just for the sake of illustration, and you want to try to predict the probability of heart disease based on cholesterol level and BMI and family history, something like that. In that case, you have several predictor variables rather than just one. And you might want to know, how can you use regression to see if there's an association between the outcome and the various predictors, and that's what we'll be discussing today. Oh, just to illustrate how this works, we'll do another quick review of linear functions. You'll recall that when we did this in the univariate case, we had this example of an amusement park where it costs $10 to get into the park and $3 to ride on a ride. The total cost of your day at the amusement park was 10 plus 3 times x, where x is the number of rides. Well, what if we wanted to extend that to a case where there's more than one predictor variable? Say that you might also want to eat hot dogs while you're at the amusement park. In addition to going on rides, then the total cost of your day at the amusement park would be 10 plus 3 times the number of rides plus 1.5 times the number of hot dogs. Straightforward enough, hopefully. And in general, you could write this as y equals b0 plus b1 times x1 plus b2 times x2. If you wanted, you could have more than two x's. You could have this up to xn. The terminology is, once again, b0 is known as the y-intercept, or sometimes just the intercept. And the b1, b2 are the coefficients, i.e. the slopes for the various variables. In this case, 3 is the coefficient for rides, and 1.5 is the coefficient for hot dogs. And in the multivariate case, the way you can interpret a slope is that a 1 unit increase in x is associated with a b unit increase in y, or b unit decrease if it's negative, if the other x's are held constant, which is a very important assumption in the multiple regression case. that in this particular example, if the number of hot dogs is held constant and you go on one more ride, the total cost of your day at the amusement park will increase by $3. But in practice, this assumption of holding everything else constant is quite frequently violated, which means you have to be careful how you interpret the slopes. If we take like our heart disease example again, that, for instance, family history is probably associated with both cholesterol and BMI. So if family history increases by 1 unit, most likely BMI and cholesterol are not being held constant, they will increase as well. Or in the amusement park example, if you're at the amusement park for a longer period of time over the course of the day, you're likely to go on more rides and eat more hot dogs. So you may not be able to hold one constant and increase the other by 1 unit. So keep that in mind when you interpret these slopes, because you can get into a bit of trouble that way. So how do you compute a multiple regression model? Well, recall in the one variable case, we try to minimize the sum of squared errors between the observed y's and the predicted y's. Take the observed y minus the predicted y squared, and find b0 hat and b1 hat to make this sum of squared errors as small as possible. In the multivariate case, you do the same thing and just estimate where rather than estimating only b0 and b1, you estimate b0, b1, b2 up to m, where you have m predictors. Choose the value of all these b's to try to make this sum of squared errors as small as possible. And the formula for calculating this is ugly. It requires a bunch of matrix algebra. I don't know if you've necessarily even seen before, so I'm not even going to bother to write it down. For the purposes of this class, to calculate a multiple regression model, you just do R and it'll calculate it for you, and we don't need to worry about the details. So, example of multivariate regression that I'll do today is from a data set built into R, which is what R calls the stack loss data. That as, I don't know much about this data other than the description of the data set in R. It's basically a data set on collecting data on the efficiency of a plant where they're trying to convert ammonia to nitric acid. That basically there's some type of absorption tower that performs this conversion, and the outcome variable they're trying to predict is the stack loss, which is basically the percentage of the ammonia that doesn't get absorbed in the absorption column. That is, it's like an inverse measure of the overall efficiency of the plant. If the stack loss is 0%, that implies that all of the ammonia is being converted to nitric acid. There's no loss in efficiency at all. If it were 100%, then all the ammonia is being lost and the plant isn't doing anything. The objective of this analysis was to see what sort of variables are associated with better efficiency in the plant. And this particular data set, there's 3 different predictor variables they thought would affect the efficiency of the plant. Number 1 is the airflow, just basically the rate of operation of the plant, how quickly the ammonia is being cycled through. The second variable is the water temperature, which is the temperature of the cooling water in the absorption tower. And then there's the acid concentration, which is basically the concentration of the nitric acid after it's converted. So, to fit this regression model in R, This data is called stack loss. It's built into R, so you don't need to import it or anything. And the outcome variable is called stack.loss. The three predictors are airflow, water temperature, and acid concentration. So to fit the multivariate regression model, the syntax is very similar to the univariate model. You go outcome variable, stack loss, twiddle. The predictors, only in this case we have more than one predictor, so we just go airflow plus water temperature plus acid concentration. In general, when you want to do a multivariate regression model, just go x1 plus x2 plus x3. And another way that you can do this that will save you typing sometimes, if you have one outcome variable and then every other column of your data frame is a predictor, rather than typing every single one of the predictors one by one, you can just go stack loss twiddle dot, where and that just says predict stack loss based on every other variable in the data set. In this case, three other variables are airflow, water temperature, and acid concentration. And you get an output that's quite similar to what you get from the univariate regression case, only in this case, note that we have three different coefficients rather than one. So coefficient for airflow is 0.1756, coefficient for water temperature 1.2953, coefficient for acid concentration minus 1.1521. And as you'll recall, the interpretation of these variables, this is saying if you hold airflow and water temperature constant, the stack loss increases by 0.7156% every time the airflow increases by 1 unit. Likewise, as the water temperature increases by 1 unit, the stack loss increases by 1.2953 units, indicating that the faster the air is flowing, the worse the efficiency of the plant, and the warmer the water, the worse the efficiency of the plant. And the T statistics and F statistics and R squared are analogous to the interpretation in the univariate case. We have a multiple R squared of 0.9136, indicating that we can explain about 91% of the variation in stack loss based on the variation in these three temperatures, indicating very good predictive accuracy. And the F statistic gives us a p-value of about 3 times 10 to the minus 9. Recall in this case, the F statistic is testing the null hypothesis that every single one of the coefficients is equal to 0. There is very strong evidence against that null hypothesis. And the T statistics, on the other hand, test the null hypothesis that any one of these given coefficients is equal to 0. So the T statistic for airflow is about 5.8 times 10 to the minus 5. Very strong evidence the coefficient for airflow is non-zero. Water temperature, the p-value is 0.00263. Still pretty strong evidence the coefficient for water temperature is non-zero. Not nearly as strong as the evidence for airflow. In acid concentration, we get a p-value of 0.344. In this case, we would probably fail to reject the null hypothesis that the coefficient for acid concentration is equal to 0. That indicates that you may be better off not even including acid concentration in the model, since the coefficient may actually be equal to 0 and not be giving us any additional information. And as I said before, if you go LMY twiddle x1 plus x2, that'll perform multiple regression on x1 and x2. If you go y twiddle x1 plus x2 plus x3 plus x4 up to plus x10, then it will do multiple regression on those 10 variables. And if you have 10 variables and you don't want to write out every single one, you can go LMY twiddle dot, to predict y using all the other variables in the data frame, you have to specify the name of the data frame that you're using for this, or else that won't work. So, went over this quickly on the other slide, that the output for the multiple regression, it will give you a t-statistic for each coefficient. It will also give you an f-statistic for testing the null hypothesis that all of the coefficients are 0. So, we saw the t-statistic in the stack loss data, the t-statistic for airflow, strong evidence that it's non-zero. Water flow, also strong but not quite as strong evidence that it's non-zero. And then we also have the S-test, which tests the null hypothesis that every single one of the coefficients is non-zero. If at least one of the coefficients is non-zero, then if at least one of the coefficients is non-zero, then the F-statistic should give you a significant result. If we saw before spring break that for the one variable case, the t-statistic and the f-statistic gave exactly the same p-values, which makes sense. If there's only one variable, the null hypothesis that that particular variable's coefficient is equal to 0 is the same null hypothesis that the coefficient for all the variables is equal to 0, because there's only one variable in that case. And now for some comments on how to interpret multiple regression models. That people who don't understand multiple regression well enough misinterpret these models all the time, and you see plenty of published papers where people get this wrong. So, and I mean, this is fairly confusing stuff that honestly there are entire classes at this university devoted to this sort of topic, so trying to inflict all this on you in 1 week is a bit cruel. But you don't need to know all the details for this class. The important thing that you need to know for this class is that you do not want to just mindlessly fit a multiple regression model, go and report the coefficients without thinking, or to the point you want to know what these coefficients can and cannot tell us. That in a multiple regression model, the p-values of these coefficients can be misleading. Sometimes even the signs of the coefficients can be completely wrong. And that you need to be extremely careful when interpreting the outcome of a multiple regression model. To be more specific, I'll have more comments on this later in today's lecture, but like every year I put at least one question on the final about interpreting multiple regression models, and every year at least half the class messes it up, and I'm ready to cry and think I'm like a total failure at teaching statistics, because every year I try to hammer on this point more, but never seems to work. So I'm going to scream about it even more this year, and assuming there is a final, which we'll see at this point, I do not want everybody to get it wrong again because it will make me sad. So, just to illustrate how you can get into trouble interpreting these multivariate regression models, here's our multivariate model for the stack loss again. See, airflow gives us a coefficient of about 0.0156, about 0.1295 for water temperature, minus 0.152 for acid concentration. We get the p-values and so on and so forth. So does that mean that if airflow increases by 1 unit, stack loss increases by 0.7156? Does that mean that as acid concentration is higher, the efficiency of the plant increases because the stack loss decreases? Does acid concentration not matter at all? Well, let's see about these things. So now let's do regression on one variable at a time. First, let's do it on airflow. And note that when we do it on airflow, we get a coefficient of about 1.02 and a p-value that's much smaller than we got in the multivariate regression model. Also note, if we look at the R squared, the decrease in R squared from the full model to the airflow only model isn't that much. We go from about 91% down to about 84.5%, indicating that airflow by itself tells us a lot about the variance in stack loss. But the interesting part is, note the coefficient got significantly larger. That it was about 0.756 in the previous case, or 0.7156. I can't read my own slide. Jumped up to 1 in the univariate model. How do you reconcile the two? Well, basically, I mean, this is confusing. I have to think about this myself. What this tells you is that if you ignore the effect of ignore the effect of water temperature and acid concentration, then 1 unit increase in airflow accounts for about a 1 unit increase in stack loss. But if you take those other two variables into account, then some of the variance in stack loss explained by the other variables and not by airflow, suggesting that airflow isn't quite as important as we thought it was. How do you interpret this in real life? If I were writing a paper on this, I mean, I would just say that, like, when we included these other variables in the model, the coefficient for airflow got smaller. That implies that some of the association between airflow and stack loss can be explained by the fact that higher airflow generally means higher water temperature as well, and water temperature accounts for some of the variation, something like that, if that makes sense at all. Like I say, this is all highly confusing, but the take-home message here is you can't just look at the univariate analysis or the multivariate analysis and think that it gives you the whole story. You should look at both, see how they change, and figure out why they change. In this case, the most obvious explanation is that some of the variation in stack loss is that water temperature and airflow are both related to one another. So once you take water temperature into account, the effect of airflow isn't quite as important. That, again, if we take the heart disease example, that if you take family history into account, maybe cholesterol doesn't seem as important as it seemed before, because some of the variance explained by cholesterol is actually due to family history, not due to cholesterol itself. And if we look at water temperature by itself, now the coefficient goes up to about 2.8, where it was around 1 before, and we get a p-value of on the order of 10 to the minus 7, whereas before it was 0.002. Also, the R squared is about 0.7665, a decrease in predictive accuracy from the multivariate model, but still of only on the order of about 15%. So what does this tell us? Well, once again, the story seems to be that airflow and water temperature are both associated with one another. If you look at water temperature by itself, it's a fairly strong predictor of stack loss, but higher water temperature is associated with higher airflow. Once you take airflow into account, the association between water temperature and stack loss isn't as strong, because a lot of the variation is actually explained by stack loss rather than water temperature itself. And acid concentration is the really weird one, that the coefficient still isn't statistically significant at the 0.05 level. It's about 0.07, but if you recall in the multivariate model, the coefficient was negative. Now it's positive 0.759. how do we explain this? It looks like there may be some weak association between acid concentration and stack loss. It's hard to say with the data set this small. Maybe it's just a fluke, but if any such association exists, it's completely accounted for once you include airflow and water temperature in the model. It doesn't appear to give you any additional information beyond what you get from airflow and water temperature is probably the way to interpret this. So like I say, I mean, I know this is not easy to see when you first look at this model, and I apologize if this is confusing. Hopefully, as you work through some of the examples and the homework, you'll wrap your brain around it, and I'll try to help you with it as much as possible. The point is, be very careful how you interpret these models. Look at the univariate model, look at the multivariate model, see the changes between the two, and try to understand why they change, if they change. So conclusions that we can draw here: airflow and water temperature both strongly associated with stack loss. Water temperature provides a little bit of additional information beyond what we get from airflow, but not a ton of additional information. And but some of the association between airflow and stack loss is actually explained by water temperature. That's why the coefficient got smaller when we included water temperature in the model. Acid concentration may be weakly associated with stack loss, but it doesn't seem to provide any additional information beyond what you get from airflow and water temperature. And it's quite common when you do multivariate regression for the sign of a coefficient to change depending on what other variables you include in the model. So you shouldn't rely on the sign of a multivariable regression coefficient to tell you the direction of an association. We saw in the stack loss data, it looks like if you look at acid concentration by itself, it's a positive association, but you throw in the other two variables in the model, it goes negative. So don't just look at the multivariate coefficient and say there's a negative association between these two, because that may not be true. And the variables that you include in a multivariable regression model can have a big effect on the final form of the model, and trying to decide which variables to include can be a tricky problem. If there's a relevant variable that you forget to include in the model, you can get a biased model and your coefficients can have weird signs. My favorite example of this that I think I've used a time or two in this class already is like the bombing runs in World War II. When they just barely invented regression at this point, we're trying to build a model to predict the success of a bombing run. And they found that planes flying slower speeds and at lower elevations were associated with higher probability of success. Okay, that makes sense. If you're closer to your target or flying more slowly, you're more likely to hit the target. Also discovered that more enemy fighters in the air was associated with increased probability of success, which when they first saw this result, they were like, what on earth is going on here? You would think having people shooting at you would make it harder to hit the target, not easier. Well, if you remember this example from earlier in this class, it left out a really important variable, namely cloud cover. That if it's a cloudy day, the enemy can't see you up in the air, so they don't try to shoot you down, but you can't see the target either, so your bombs are all over the place. Once they included a variable for cloud cover in the model, then the coefficient for fighter opposition became negative, as you would expect. Oh, the point is, if you forget to include a relevant variable in the model, it can bias your model. In extreme cases, it can make your coefficient estimates and hence your t-tests and confidence intervals completely meaningless. A real-world example that's a bit more relevant to the bench science world is a study that I was working on to try to identify risk factors for temporomandibular disorders, i.e. TMD. And this study, we believe that TMD patients would show heightened sensitivity to thermal pain. So our study protocol was we put a thermal probe on people's arms and heated it up to a high temperature once every 3 seconds and repeated this 10 times over a period of about 30 seconds. Each time we turned on the heat, we asked them to rate their pain on a scale from 0 to 100. And we summarized these results into 2 predictor variables. Looks like keynote cut off the bottom of my slide. That one was their pain rating at time 0, the pain rating we first turned on the temperature, and the second variable was the rate that their pain ratings increased over time. The belief was that people with TMD would be more sensitive to pain, so their initial rating would be higher than TMD-free people. They would also, what we call, wind up more. That is, that when you burn them repeatedly, they would report a greater increase in pain over time than TMD-free individuals. So we fit univariate regression models to predict the risk of having TMD based on these 2 variables, the initial pain rating and also the rate of increase. And the initial pain rating was associated with TMD, but the rate of increase was not associated, which we were scratching our heads about initially. But when we put both variables in the model, suddenly both of them were strongly statistically significant, which was kind of weird. And basically, we looked at the data a little more closely and finally figured out what's going on. There's 2 different ways you can have high risk of TMD. One, if your initial rating is high, you're at higher risk of TMD. And if your initial rating is high enough, then it's hard to get a significant increase in your pain rating over time because you're already high in the first place. The other way to have elevated risk is if your first pain rating is low, but your pain rating increases rapidly over the 10 thermal pulses. So, when we fit the multivariate model to take the effect of the first pain rating into account, suddenly the rate of increase variable became significant. And this is what's known as an interaction that we'll discuss in more detail in a later lecture. The important take-home message here is when we didn't include the first pulse rating in the model, we got a biased result. We thought that the rate of increase wasn't significantly associated with TMD, even though it actually was. And so, if you can be biased, if you leave important variables out of the model, does that mean that you should just take every variable that you possibly can, throw them all into the model to make sure you're not overlooking anything and getting biased results? Well, unfortunately, it's still not quite that simple. If you include an irrelevant variable in your model, in general, you still won't get biased results, but it will increase the variance of your model. So you'll get wider confidence intervals and more conservative p-values. And depending on what you're trying to do, you may not care. My study of TMD that I just described has over 3,000 people in it. So if we increase the variance a little bit by including an irrelevant predictor, well, that's not so bad because having a sample of size 3,000 decreases the variance of your sample a lot. But if you have a really small sample size, then you're going to have a high variance in the first place. You don't want to include irrelevant predictors that could increase your variance even more. And in general, if you're reasonably confident that a variable isn't relevant, you should probably leave it out. And how do you tell if a variable is relevant? Well, the correct way to do this, that nobody actually does, is on this slide. I'm going to teach it to you just in case you're ever working on a problem where it's important to formally test this. Say you want to know, say you have a bunch of variables x1, x2 up to xm, and you want to know if x0 gives you any additional information about y after taking these other x's into account. The correct way to do this is, first of all, you regress y on all of the x's except for x0. Then you regress x0 on all of the other x's. Then you try to predict the residuals of the first model based on the residuals of the second model. If there's a statistically significant association between these two sets of residuals, then it's safe to conclude that x0 gives you additional information beyond the other x's. If you didn't follow all that, don't worry about it. I mean, like I said, even though every elementary regression class says that you should do this to see if additional variable adds information in your model, nobody actually does this. What people actually do is they just fit a multivariable regression model where they just say x0 plus x1 plus 2 up to xm. That gives you regression output with a coefficient for x0, an associated t-statistic, and p-value. They just look at that t-statistic. They just look at that p-value. If it's less than 0.05, they conclude that x0 adds information. If it's greater than 0.05, they conclude that it doesn't. That's technically wrong. You can construct examples where this will give you incorrect results, but in practice it's not so bad. You can construct examples like that, but usually you won't get into trouble with this approach unless you deliberately go out of your way to try to break this. Most of the time it will give you the same result as the complicated residual thing that I described on the previous slide, and it's a heck of a lot easier to do. So I think every paper that I've ever read in my entire life just does it this way. I mean, I remember when I was in grad school and working on one of my first collaborative projects, we wanted to answer this question like, does genetics increase the risk of developing a certain type of leukemia beyond known prognostic factors? I wanted to do the formal thing with residuals. My advisor was just like, Eric, nobody does that. Do it this way. So we did it that way, and we still got into the New England Journal. So, you know, whatever. But one thing to keep in mind is that one thing that you cannot do is simply add the new variable to the model and see if r squared increases. Because by the definition of r squared, it will always increase when you add more variables to the model. So the fact that r squared goes up when you include an additional variable doesn't tell you anything. At the bare minimum, you need to look at the p-values for the variable that you just inserted in the model. So should we just include all the relevant variables in the model and exclude the variables that are redundant? Even that doesn't necessarily give you the best model due to a problem known as multicollinearity, which I'll illustrate here in a second. That multicollinearity is that if you have several different x variables, several different predictors that are highly correlated with one another, then adding more x's into your model doesn't give us much information. That, like the stack loss data, for instance, water temperature by itself was a very strong predictor, but once we included airflow in the model, water temperature gave us a little more information, but not very much. And every time you add a variable to a model, it'll increase the variance of your model. So you can reach the point where if you have a bunch of predictor variables that are strongly correlated with one another, you start adding more variables to the model. Since they're so strongly correlated, they give you no additional information about the outcome, and they also increase your variance as you put more things into the model. So you add too many predictors to your model, you can actually get worse predictions than if you had fewer predictors. A famous example of this is a data set called the Longley Data, named after the economist who collected this data set and illustrated this example. It's also built into R. This particular economist was trying to predict the employment rate based on various factors that are known to affect the employment level, i.e., like the gross national product, the total population of the US, and things like that. And the variables he looked at are ridiculously strongly correlated with one another, making the regression model really difficult to interpret. So here's when you mindlessly fit a multivariate regression model in R to the Longley data. The data is called Longley, and the predictors are two versions of GNP, the unemployment rate, the number of people in the armed forces, the total population of the country, and the year. Immediately you look at it and there's a couple strange things that, like, there doesn't appear to be any association between GNP and employment. And you might say, okay, what gives with that? You would expect GNP is large, the economy is stronger, unemployment should be lower, but we don't see that. Well, this is an extreme example of multicollinearity causing major problems. That, first of all, how do we know that there's multicollinearity in the first place? Well, there's this command in R called pairs that I'll show you in a second that will plot every set of pairwise scatter plots. Recall that, like, multicollinearity means that the predictor variables are associated with one another. And you look at, like, GNP deflator and GNP, it's almost a perfectly straight line. Likewise, if you look at, like, population and year, even like unemployment and GNP isn't a perfect straight line, but are pretty strongly associated with one another. If you see linear patterns in the pairwise scatter plot like this, that tells you that your predictor variables are all correlated with one another, and that multicollinearity may be a problem. That if you have GNP in your model, you can predict GNP deflator with almost perfect accuracy. So putting both GNP and GNP inflator in your model doesn't give you any additional information. In fact, it probably makes your model worse by increasing the variance of your model. And the pairs command in R will plot the set of pairwise scatter plots. It's a useful trick if you're trying to see if your variables are correlated with one another. And so multicollinearity means that it's a bad idea to just take every possible relevant predictor variable and stick it in your model. Finding the best set of predictors is a really tricky problem, and in fact, not a solved problem at all. Trying to figure out the best way to figure out which variables to stick into a regression model is something that keeps people like me employed. So I'm definitely not expecting you to do a perfect job of this in this class. What I do want you to know is the dangers of using multivariate regression. If you have several predictors that are associated with one another, you should not just stick all the variables into a multivariate model, because that model may not be optimal. Another important warning here, and if you don't get anything else out of the lecture, please remember this, because it makes me sad when people get this wrong on the final every year. As I noted earlier, when you have multicollinearity going on, the t-statistic, if you want to know, answer the question, is X associated with Y? If you put X in a multivariate model with a bunch of other X's, the coefficient for X can be non-significant, even if there is a very strong association between X and Y. As you'll recall, the multivariate model on the Longley data the coefficient for GNP was not significantly different from 0. Well, we do a univariate model on GNP alone, we get a p-value of like 10 to the minus 12. GNP is actually very strongly associated with the employment rate, despite the fact that the coefficient was non-significant in the multivariate model due to multicollinearity. The multivariate model tells us that once we have like population and armed forces and all that other stuff, GNP doesn't give us any additional information, but by itself it's still very strongly associated with employment. So, if, very hypothetically speaking, I give you a final question where there's several different columns of data and I say, which of these variables are associated with the outcome? Do not stick all of them in a big multivariate regression model, see which ones are significant and say, GNP isn't associated with employment because it wasn't significant in the multivariate model. No, wrong. Please do not do this. And the multivariate model can give you misleading results if they're correlated with one another. As I say, I've put this on the final every year I've taught this class, and every year I've taught this class, at least half the people in the class have made this mistake. So now I'm putting it in like big bold letters. Please, please do not mess this up again. I want to feel like I'm not a total failure as a teacher with my students making the same mistake over and over again. So, yeah. Hopefully I've made that point clear enough now, and hopefully people watch this on YouTube, so people who aren't here today don't make that mistake. Anyway, we're out of time. Things to remember for today: that you can generalize regression to cases where there's multiple predictors. You have to be very careful interpreting these multivariate regression models. Don't rely on your multivariate models to tell you if there's an association between X and Y, because it's very easy to find cases where X and Y are strongly associated, but the association disappears in a multivariate model. And trying to figure out which variables to include and not include in the model is a really tough problem. We'll discuss this in a little bit in future lectures, but it's hard. And here's the new R commands today, commands for fitting multivariable regression, and also the command for plotting pairwise scatter plots. Any questions about anything today?
So, saying that something is directly or like negatively or positively correlated to something can only be, we can only say that from a univariate model.
The question was whether you can only say if X and Y are associated based on a univariate model, and that's a good question. In general, I would say yes, but it depends. Like, I'm trying to think of an example of this. Say, like, you're trying to find the association between, let's take heart disease again, and say, is there an association between height and heart disease? Most likely, if you just mindlessly did the univariate association, then you would find that no such association exists. But that if you did a multivariate model including gender, given that men generally have higher risk of cardiovascular disease than women, then height would probably wash out. So in that case, if you just wanted to say, is height associated with cardiovascular disease? Well, yeah, then you should do the univariate model to answer that question. But if you wanted to answer the question, does height give you useful information about the risk of developing cardiovascular disease? In that case, you would probably want to control for gender. And if you control for gender, then it probably doesn't. So it's heavily context dependent. But in this class, I don't intend to do anything that confusing. This is just for your own enlightenment as you write papers and so forth. If I give you a question on the final saying, is X associated with Y, just do the univariate analysis, unless I specifically say adjusting for this particular confounding variable. Yeah. when we write papers on this, we always adjust for like gender and age and stuff like that, just because they're confounded with so many things, and we don't want to publish an association that's just a confounder for gender or age or something. But in general, you want to look at the univariate results, and you certainly don't want to look at multiple putative risk factors that are not known to be confounded with one another. Does that make sense, kind of? Okay. Other questions? Sorry for keeping you over.